Okay, so this chapter is dealing with electrostatics. Electro for electricity, which ultimately comes from the word electron, right? So motion of electrons creates electricity, or is electricity. And electrostatics, static has to do with static, stationary. So electrostatics typically deals with electrons, charges that are stationary. This is different from electrodynamics, which talks about electrons, charges that are moving, and the two fields have similarities and some dissimilarities. So electricity is a general term for electrical phenomena related to charge, usually motion of charge. Electrostatic is a study of electric charge that is at rest, that's not in motion. If it is in motion, you end up with electric currents. Introducing the concept of conservation of charge. Conservation of charge basically means that charge is conserved, which basically means that charge cannot be arbitrarily created or destroyed. Just like we've talked about conservation of energy. Energy cannot be created or destroyed, right, by any physical entity in our universe. So similarly, charge cannot be created or destroyed by any physical entity in our universe. Next slide. These are concepts that you're all familiar with. If you have two positive charges and you bring them together, do they experience an attraction or a repulsion? A repulsion, right? So here you've got a charge sphere that's tied by a string to the ceiling, another charge sphere tied by a string to the ceiling, and what happens is you put them close to each other, the positive charges repel each other. Why is this the case? We don't know. We just take it on faith and move on, right? Now if you have two negative charges, they also repel each other, they push each other apart. On the other hand, if you have opposite charges, they attract. Negative and positive, they attract. Why do they do this? We don't know, right? Take it on faith, move on. Coulomb's law. The relationship among electrical force, charge, and distance. We said that if you have a positive charge and a negative charge, they are attracted. What's happening is there's a force that's pulling them together, right? There's a force that's pulling them together. We can measure the strength of that force. That force is given by this expression. Force equals K, which is a constant, multiplied by Q1, which is the value of the charge, the first charge, multiplied by Q2, which is the value of the second charge, divided by d squared, the distance between the two charges squared. This expression is very similar to the expression that we saw for gravity, right? Where if you remember gravity, the force was capital G, which was a constant, multiplied by mass 1, multiplied by mass 2, divided by distance squared, right? Which is a really interesting coincidence, if you will, that they both behave in such a similar fashion. Now this force will be positive or negative depending on whether the charges are the same sign. If they're the same sign, then it's repulsion, so it's a negative force, if you will, or a positive, depending on your coordinate system. And it's the opposite sign if they're opposite charge signs, like my negative versus positive. Now, I talked about the quantity of charge, Q1. That is expressed in units of coulombs. A coulomb is a unit of electrical charge where 1 coulomb is equal to the total charge of 6.25 times 10 to the power of 18 electrons. Right? So what the Earth has, let's say 6 billion humans. So you would need, 6 billion is how many, 10 to the power of what? 10 to the power of 9. So you would need a billion Earths. A billion Earths, replace each human being with an electron. Gather all those electrons, add the charges due to all of those electrons, and that gives you 1 coulomb worth of charge. Okay? Introducing the concept of conductor and insulator. A conductor is a material like this, like a metal, that conducts electricity. The atoms in the metal do not hold the electrons very tightly. So when I apply a voltage, the electrons move easily, and so it conducts electricity. That's the top item. The next item was an insulator. An insulator is a material where the atoms hold on to the electrons very tightly. And so what happens is I can apply a voltage across an insulator, like a pen or a pencil or something. Right? The wood of a pencil is an insulator. So I can apply a voltage across, or the plastic of this pen is an insulator. I apply a voltage across this. What happens is the plastic, the atoms are holding on to the electrons. They don't let go. And so even though I apply a voltage, the electrons don't move. So you don't have a current flowing. Right? Okay. Now, charge can be transferred from one object to another, in this case by contact, basically by rubbing something. So here you could have a stick of plastic, like a rod of plastic or ebony or something of that sort, and you polish it with a particular, like with silk or with fur or something, and depending on the particular combination of materials, you will end up with charge being transferred from the plastic rod or the ebony rod or whatever to the cloth. So the rod was initially neutral. You polish it with this silk or whatever. Now what happens is you end up with electrons. This is now negatively charged, which means you have electrons here. Where did the electrons come from? Came from the cloth, which means the cloth has to be positively charged because it gave up electrons, right?
So when you're in the store and you're pushing the cart,
yes,
is it the cart that is getting transferred?
you're talking about static electricity,
Yeah.
right? Or you walk, like depending on your shoes, you walk on carpet, right? And then you go and open the door and you get a... It depends on the combination of materials. So sometimes it'll be that you get electrons, sometimes the other, like you can either have an excess of electrons or a deficit of electrons. So you can get positively charged or negatively charged. Depends on the combination of like your shoes and whatever material combination. Like in the case of a cart, it could be the plastic of the wheels, like the wheels are like some combination of rubber and plastic, plasticized rubber or rubberized plastic or some combination. And that particular material interacting with whatever linoleum or whatever it is they have will end up with transferring charge. And that could be electrons being transferred one way or the other. Depends on the combination of materials, right? Do you?
Yeah.
Yeah.
I noticed
I've
with me, it's like the shampoo I use
okay.
would do that, so I switch and it doesn't happen anymore.
Okay.
I don't know, I guess that's just me.
Yes, I mean like particular shampoos can leave residue in your hair that has a tendency to get positively or negatively charged, right? Or is less conductive or more conductive. If it's more conductive, it'll neutralize the charge more easily, right? So anti-static stuff that you put in your dryer, similar, yeah, is along a similar, because particular kinds of clothes that you wash and put in the dryer, because of the friction associated with the tumbling, can have charge transferred by a similar phenomena. So you put this static sheet, and what happens is it dispenses some kind of a chemical that increases the conductivity. That's one way of doing it, that prevents charge from accumulating, right? Okay, so introducing the concept of induction. In the case of induction, you're inducing a charge. So here, the way you look at this is a metal sphere, another metal sphere on a insulating rod, like a rubber rod or a plastic rod or a wooden rod on a base, right? Now what happens is A and B are in contact. Now you charge up one of those rods by rubbing it with silk or fur or something, and you've got a negative charge on it. You bring it close to, don't touch it, but you bring it close to this sphere A. What happens is now, because both of these spheres are conductive, the negative charges here attract positive charges on the side and repel the negative charges. So electrons in these spheres travel to the other side. They move away. Now while you're holding B stationary, you move B apart from A. So B is no longer in contact with A, and now you take away the rod, and what happens is A has become positively charged and B has become negatively charged. Right? You didn't put any new charge into the system, because notice that you have not touched this. All that you did is you attracted the positive charges to one side and the negative charges to the other side. And that is called induction. Now we talked about friction possibly creating charges or separating charges. Something along those lines can happen in a cloud, right? Cloud is basically a mixture of moisture. The atoms are doing their things. So you can end up with a cloud being positively charged on one side and negatively charged on one side. This can then induce a positive charge here. So this can result in lightning from the cloud to the earth. In principle, you could have lightning from the earth to the cloud. In principle, it's more common. My understanding is it's more common from the cloud to the earth. Now you also have probably seen that there's lightning from cloud to cloud. So you have another cloud that's, let's say it's hanging out here, and that's all negatively charged. You can have neutralizing of these charges by lightning zap from here to there or from there to there, right? So this is basically making the point that in many tall buildings you end up with these pointy spikes that you put at the top with a cable that goes down to the earth. And I used to think that this is lightning arresters, right? I used to think that this was intended, so if lightning hits the building, you wanted to hit the spike and travel down the outside of the building to the earth instead of going through the building and killing people and burning the building up, right? But what the textbook tells us is that the purpose of these spikes is actually to dissipate the electric charge that builds up here. Because if you have a spike, sharp spike, you end up with a high electric field and it can dissipate into the air more easily, right? Maybe that's true, but that's what the textbook says. Okay, introducing the concept of electrical polarization. Polarization is a separation, right? So, typical atom here, you've got the positively charged nucleus, and around it you have the negatively charged electron cloud. The combination of the two of these is electrically neutral. If you put this atom in an electric field, what happens is you can get the nucleus to stay here and the electron cloud gets pulled in this direction. So let's say I place a positive charge here. So the electron cloud gets distorted. So now the center of the electron cloud is no longer at the same place as the center of the nucleus. In this case, what happens is now there's a charge separation. This atom has become polarized. You've created what's called a dipole. It's got a positive pole and a negative pole, right? So it's called a dipole, and that's polarized. So you can have a sheet of material, like a sheet of paper or something like this. You get one of those rods that you charged, you made negative, bring it close to the sheet of paper, and what happens is all the electron clouds in the atoms move away from this charged rod, because this is negative, so it's driving away the negatives. You end up with all the negatives on one side and right with each of these atoms, and positives along here. So now you've just created a net positive charge on the side of the paper, a net negative side on this side of the paper. And this is, if you've ever seen this little parlor trick done, tear up little pieces of paper, take a plastic comb, run it through your hair, and then bring the comb down to those little pieces of paper, and you can see the paper will get attracted to the comb. You ever done that? Seen it, right? Yeah, that's the same phenomenon. Basically what's happening is when you put the plastic comb through your hair, you're transferring charges. Your hair gets charged, the plastic comb gets charged. Now when you bring it to these little pieces of paper that you've torn up, the paper gets polarized like this. So if the comb had become negatively charged, you end up with positive charges here. This creates a force, and the little piece of the paper is small enough, it'll actually get attracted. It'll jump up to the comb.
How does he know one's negative or positive charge? That can only negative or positive.
Yeah, that's a good question. Extra credit to you if you can look it up. What we do know, I'm sorry?
Wikipedia, I guess.
Wikipedia will work, right? So ask the question, like, why is it that a particular combination of materials, it's a combination, it has to do with the specific materials that are interacting. Like you take ivory or ebony, like the wood, right? And you polish it with silk, it gets charged one way. You polish it with fur, it gets charged another way, and so on. And I haven't looked into that question to be able to answer your question. My guess is it may have to do with something called the work function, which is the energy associated with how much energy do you need to put into the system to get the electron to leave that atom. And that work function is different depending on the different materials and so on. So if one has a higher work function compared to the other, here's a possible hypothesis. Then we also have the electronegativity. If you have taken the chemistry, right, you know that different atoms are more or less electronegative. So you can have a more electronegative material interacting with a less electronegative material, stuff like that. So, but that's a good question. Did you have a question, or?
Yeah, I think I just answered it. I was just wondering why it would pull up the paper and why it wouldn't be equally pulled both ways, but that's...
Yeah. Okay, good. Extra credit for the question. Yeah, so here's what I talked about, right? Comb through your hair, becomes positively charged, bring it close to the little piece of paper, and this becomes negative charge on this side, positively charged on that side. But since the force is inversely proportional to the distance square, the force of attraction from here to here is much greater than the force of repulsion from here to here. So there is a repulsive force, but the net force in the paper is this larger force minus that smaller force. So the paper gets attracted, right? The same thing if you've ever done this, like if you've got kids at a party or something, like little kids get a kick out of this. Take a balloon, you rub it on somebody's hair, right? And then you stick it on another kid and it sticks, whoa, right? Or you can stick it to the wall. And what's happening is this. You rub it on the person's hair, the balloon gets charged up negatively. Now bring it to the wall, and what happens is the negative charges in the wall get repelled, so they go away to the other end, becomes positively charged, and the balloon sticks. as long as charge doesn't leak from here to here. If charge leaks from here to here, then it'll neutralize the charge and the balloon will fall off. This is why after a while the balloon will fall off. Yes, sir?
How powerful is that?
That force?
Like when you put the balloon on the wall, is it sending every single negative charge that the wall has away from it?
No.
Or it's just some of them because it's a pretty weak charge?
Yes.
Okay.
It's not very strong. Right? Okay, electric field. We've talked about gravitational field, right? That the earth attracts us to it. Similarly, we've talked about the fact that a negative charge will attract a positive charge. So, here's a negative charge, we're trying to plot the electric field of the negative charge. So place a positive charge here, there's a small force pulling it towards a negative charge. So this, you draw this little arrow here. If you put the positive charge here, there's a little arrow pointing in that direction. Put the positive charge, little arrow pointing in that direction. Now if I take that same unit positive charge and place it here, the arrow is bigger, same direction. Move it here, the arrow is even bigger because the force is bigger, right? And you're pulling in. So by doing this around that, you can actually chart or plot the electric field. So in the case of a negative charge, the electric field is pointing inwards, because the electric field is a representation of the force that a positive charge experiences if placed at that location. So this is why the electric field here is all pointing in. In the case of a positive charge, now if I were to place another test positive charge, unit positive charge here, it experiences a force pushing it outwards. So I end up with this arrow outwards. If I place the positive charge here, the test charge, it's outwards, 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 outwards. So all of these are outwards. If I create a dipole, which is where you've got a negative charge and a positive charge, what happens is these, you could call these field lines. They're lines that represent the electric field. The field lines, they come outwards from the positive charge, they go inwards into the negative charge, and they curve around from the positive to the negative charge. The field line describes the trajectory that a positive charge would experience if placed here. So here's a positive charge, here's a negative charge. I take a unit positive charge and place it here. That positive charge will get repelled by this charge, so it'll move away, but it'll move along this line. It'll come over here and suddenly realize, there's a negative charge there, I want to go there. And it'll start moving here until it collides with that. That's what the field lines represent, right? Anywhere on a field line, place a positive charge, the positive charge will be moving along that field line. It'll move away in the direction of the arrow that is drawn in the field line. So if you have two positive metal plate and a negative metal plate, you end up with all these field lines going parallel, right, or perpendicular to the plate from here to here. You can actually, you've probably done this in high school or in elementary school, where you take a sheet of paper, you place a charge or a magnet on one end and a magnet at the other end, or a charge, sprinkle iron filings, and you end up with a distribution that looks like this. The iron filings, they line up along these field lines. So here is an actual representation where you can see the field lines, right, between a positive charge and a negative charge, or between a plate and another plate. So this is positively charged plate, negatively charged plate. You see all the lines, right, lining up here, and away from here they are kind of curving off. So the electric field is defined as the force per unit charge, right? Okay, 3 slides. Should we do it or hold off? Hold off? Okay. I know this is a lot of material. So let's go ahead and end this lecture now, and you can go ahead and start the lab.